Okay, I'm going to talk for a minute about curve fitting data. And so I've got a set of data here that I could have obtained many different ways, but this data actually comes from the lift and the pitching moment here, come from a vortex panel method, a vortex panel code that uses a vortex strength along each panel that varies linearly, and then we're satisfying the cut condition at the trailing edge. And this comes from a 2412 airfoil that I've modified a little bit to close the trailing edge. And then I've also used X-foil. So a panel code will not give you drag because drag is 0 for an inviscid airfoil. But from X-foil, I've gone through, and for the 2412 airfoil, I've pulled out drag coefficients at these different angles of attack. So here we have lift, pitching moment, and drag as a function of angle of attack, but really this could be any data set that you want to work with, and the principles that we're going to learn here for curve fitting would be the same. Okay, so what I'd like to do is I have equations from theory that say that the lift should be, for example, a linear function of angle of attack where I have a lift coefficient, or excuse me, a lift slope, CL alpha times the angle of attack minus some zero lift angle of attack. So this comes from thin airfoil theory, and also from thin airfoil theory we get this theoretical equation for the pitching moment about the leading edge as a function of the pitching moment at the quarter-chord and the lift coefficient. And then there's also an equation here for drag that theoretically it's a quadratic or a parabola as a function of lift. So we're not going to look at this this pitching moment equation. The principles again that I go over here are the same, but we are going to look at the lift and drag here for just a minute. So just to start things off, let's look at what a plot looks like of the lift coefficient as a function of angle of attack. And so we can see that this data, again, this is a bunch of data points actually. In fact, maybe I should, let's change the chart type to show that it is a bunch of data. So there we go. Those are our data points. And you might be thinking, well, we can just fit a trend line to that, right? That's built into Excel and into multiple spreadsheet codes. So let's try that here for just a second. We can add a trend line to that data. And in the trend line options over here, we can choose if it's a linear trend or logarithmic polynomial or moving average. And there's some other options here that show up with the right data sets. So we can go to polynomial and choose a higher order, but this is just a linear trend. We're expecting a linear trend between angle of attack and lift coefficient, and so it's fit that there for us. And then we want to see what that equation looks like, so I'm going to display the equation and the r squared value on the chart. So these are so there those values there. So we can see that. Maybe I'll zoom in here just a little bit. That might help. We can see that we've got some coefficient here out front proportional to x, where x is here on the x-axis, or we've used angle of attack in degrees on the x-axis, and then plus this offset. So this is helpful if we want to get a quick equation that will go through this data. But this doesn't really help. Well, I can back out then my coefficients here. See, really what I wanted was a lift slope and a zero lift angle of attack. That tells me some characteristic about this airfoil, which we can back out from this, but it takes a little bit of work. So, for example, I plotted this as a function of angle of attack in degrees, not radians, and this equation, it assumes that alpha is, well, it will work for degrees or radians, but usually we use this in terms of radians. So I could make a new plot or a new column over here. In fact, I'll just do that of alpha in radians. And it's simply radians of that column there. Okay, so now I've got it in terms of radians, and I'm just going to change this plot here to now use radians on the x-axis. The problem with that is that it's not quite as intuitive, and now I'll again, what I want to do is add a trend line and display the equation and the r² value. Okay, so this now gave us a 6.8915 as the lift slope in radians. But then to get alpha L0, we actually need to divide this 0.2578 by this 6.8915, or we need to divide that out of it in order to get alpha L0 because it's multiplied together here in this equation. So again, it's going to take us a little bit of work to back out what these coefficients are. And that gets worse when we go to other types of equations. So for example, in a minute here, we're going to use this equation here for the lift, which is quite a bit more complicated. This is no longer a straight line, and in fact, it doesn't match any of the options here that we have for a trend line. So when you're going to use a trend line, you're really limited in the types of equations that you can fit to the data, and you're also limited on the output of that. It's going to take some work to back out the coefficients that we like to see these equations in, and so that would be especially true for this down here. And we obviously won't use this trend line method in order to fit these coefficients. So let's look at another way of fitting a trend line rather than just using the built-in function there. So what I'm going to do is I'm going to say I need to solve for CL alpha. That's my lift slope down here, and I also need to solve for an alpha L0. Okay, and I'm just going to guess at what those values are right now. CL alpha is usually very close to 2 pi, so I'm just going to put in a 6.28. And an alpha L0, I'm just going to guess a 0 for the time being, my zero lift angle of attack. And if these were my values, then my lift coefficient as a function of angle of attack, I can just put in that equation there. So it's going to be CL alpha, and I'm going to freeze that cell there, times, so I'm just typing in this equation here. So we've got CL alpha times alpha in radians, so there's my radians, minus alpha L0, and I'm going to actually put that in degrees, so I'm going to need to change that to radians, like that. So I'm going to say that this alpha L0 is in degrees, simply because it's easier for me to think of what that means. Okay, so if that was true, then at this angle of attack, minus 10, which that's the value in radians, then I would get this lift coefficient, which you can see is a bit off. And I'm just going to drag this down and look at, those are all of the lift coefficients that I would get as a function of angle of attack over here using this equation and these coefficients there. So let's look at what that result looks like. So I'm going to plot both of these lift coefficients right on top of each other as a function of angle of attack. And I'm actually going to make them both into lines. So you can see, here's the blue one here. That's our original data. And here's the orange one, and it's off a bit. So from this, we could back out some things. We could say, oh, the zero lift angle of attack looks like it's more like minus 2.5 degrees. Oops, minus 2.5. Let's see. Oh, I must not have. Yep, I didn't freeze that cell there, so it's not changing all of them like it should. Okay, there we go. So I had it at 0. And you can see that's where it was. It was passing through that zero lift angle of attack of 0. And now I could say, well, from the data, it looks like it's more like minus 2.5 degrees. And so that gets me closer. And now I can see that the slope is off. It needs to be higher than that. So, maybe I want to try 6.5. Anyway, we could iterate back and forth on this. and try to solve for these coefficients that then give me a really nice match to this data. But there's a way to automate this process, and that is by computing the error in my current solution. So I'm going to have an error column here, and I'm going to say that it is equal to the actual lift coefficient minus my guess for the lift coefficient. And I'm actually going to square that because I want to compute the root mean square of all of this error. So I'm squaring each of those values, and now the root mean square is going to be the square root of the average of all of these because I squared those. Okay, so that's my RMS for my current guess here for what those values are. And then I could continue to iterate on these values until this RMS got as small as it can, which could take me quite a bit of time. So what I'm going to use is a tool called a solver. So if you go into data, I've got this solver tool here. Now this is an add-on to Excel. It's free. All you have to do, and it's different for Mac or Windows, depending on what operating system you're on. So I'm not going to walk through that, how to get this add-on, but it's very simple. You can just Google it and choose it as an add-on within Excel, and it just pops up. It's already built into Excel. You don't have to download anything new. You just have to set it as a usable add-on, and then it will appear here in your toolbar. So so I'm going to use that solver, and it box pops up with a bunch of options in it. So the first thing is an objective cell. So our objective cell is the cell that we're trying to minimize or maximize or set to a certain value. So my objective cell is going to be the RMS. I want to minimize that RMS, and I could choose to maximize the RMS instead, but I want to minimize it, or I could try to find the solution where that RMS is a certain value. And there's different times when you'd want to use each of these. Most of the time I'm minimizing RMS when I'm fitting a function like this. And then I want to do it by changing the cells, these two cells right there. The inputs to those two cells, I want the solver to be able to change. Subject to constraints, we don't have any constraints. And then actually the first time you start this checkbox is going to be checked, and it says to make unconstrained variables non-negative. I don't know why that's the default, but you want to uncheck that. And then the solution method that I usually use is just this GRG and nonlinear, and it's got a bunch of options. And when you come into the options, you're going to see that you have a constraint precision. I usually increase the precision on these. Actually, because this is the constraints, that's not going to matter on because we're not applying any constraints here. But I like to add a few more zeros to what they have here. Their precision is set to pretty big numbers in my opinion. Same with the convergence. So usually I think when this first starts it only has I think 2 zeros, and I add in a few more, so this is more like a single precision convergence. And also the default is to use forward finite differencing for derivatives, and I like to use central because central is more accurate. So anyway, by changing a few of these things, you'll increase the accuracy of your solution. We're not going to use multi-start, so I won't cover that. Okay, so so now at that point I've got this all set up, and I just click on solve, and you can see down here in the left it will say setting up the problem, and then if it takes it a bunch of iterations, you'll be able to see it count through iterations down in this bar down here. But it says, okay, it found a solution. Do you want to keep the solver solution? And I say okay. And so now it has these are the numbers that it found for CL alpha and alpha L0 that minimize the RMS. You can see my RMS dropped from 0.05 from my guess down to 0.0018, so that's down quite a bit. And then you can also see that my two lines now are falling basically right on top of each other. And so anyway, these now are these coefficients that minimize the RMS for the lift coefficient. So we could walk through that same process for drag and come up with these different coefficients that minimize drag. It turns out though that these are going to be identical to those that you would get, you know, if I walk through this process and I define a CD0, CD1, and CD2, here, and then I write the equation for drag and the error, and then minimize the RMS. Turns out that you'll get the exact same solution as you would by simply fitting a polynomial, remember, from the trend line. So let's look at that again. So here's my drag, and I can simply add a trend line because all I'm doing is fitting a quadratic there. This is a polynomial of order 2, and so there it did it really quickly. I can display the equation on the chart and the R value if I'd like. However, this doesn't give me an RMS. I need to go back and compute what the RMS is, but those are my coefficients there, the CD0, the CD1, and the CD2, or excuse me, CD0 is down here, the 0054, the CD1, and then the CD2 proportional to x squared or CL squared. Okay, so so you can do it that way if you'd like, or you can walk through and use a solver, the solver tool to come up with those. But then using the solver tool though gives me the opportunity to also compute the RMS though, instead of just this R value here that we get from the trend line. Okay, so that's the lift and drag. So these two examples here are linear and then this quadratic, so it's not really apparent why you would want to use the solver over the built-in trend lines, because these examples are very simple. But sometimes we have more complicated functions that we want to fit something to, and so I'm going to show you that. I'm going to show you how I would fit this lift to this equation here. Okay. So so we're going to need, let's just do it right here. So what I need here is a CL0 alpha. There's some coefficient out here that's a constant. So I need to solve for that. And then sine alpha, I know what alpha is. It's in degrees and radians right there. And then minus tangent of alpha L0. So I still need an alpha L0, and I want to know what that is in degrees. And then a cosine of alpha here, which we know what that is. Okay, so this is my lift equation, and I'm just going to put, this is the traditional lift, and I'll call this my new lift. This is that new equation down here that I'm going to fit this to. Now this equation actually comes from a method called conformal mapping. You can prove from conformal mapping that your lift as a function of angle of attack actually follows this equation below stall, or the inviscid, I guess I should say. An inviscid solution should follow this equation exactly. Now this equation came from thin airfoil theory, and you can see that now again this data here came from an inviscid panel method, and we saw that we could get the RMS down to this value here. But theoretically, you know, the theory says that this is the correct equation for lift as a function of angle of attack, and so this equation should fit it perfectly and have 0 RMS. So we're going to check that out and see if that really works. So my new lift equation is equal to whatever I have for this parameter there, CL alpha. I'm going to freeze that cell, times the sine of alpha in radians, which I have over here, minus tangent of radians alpha L0, which is right there. I'm going to freeze that cell. Okay, so we've got that, then times cosine of alpha in radians right there. Okay, so that is my theoretical equation for lift, and I'm going to drag it down for all of my data, make sure that those are referencing the correct cells, and now I'm going to again compute an error in that equation, and that will be equal to the true lift coefficient minus my guess for what that lift coefficient is squared. And then I'll copy that down, and again I want the RMS over here, so I'm going to drop that there. So this is now the RMS of that column of data there. Okay, now I'm getting zeros for all of my lift, and that's because I have 0 for both of these parameters. So again, I'm just going to start with a guess of 2 pi, somewhere close to 2 pi for that 0 lift angle of attack, or or the lift slope. And then a zero lift angle of attack, again, I'll just start at 0. And you can see that I've got quite a bit of RMS error. Now let's plot, let's plot my lift coefficient here and my new lift coefficient here. Okay, and again, you see that we're off by a bit, and again, I could manually change these values until that RMS, was minimized. But I'm going to let the computer do that with the built-in solver function here. So again, I go to Data, Solver. My solver box pops up, and this time, what I want to do is minimize this RMS cell right there. And we want it to minimize, and we want to change. We want to do that by changing these cells right there. Okay, now it saved all of my previous settings, so you can go in and see that with the options, the derivative is still set to central, and I've got a pretty low convergence value on there, so that's good. So I'm going to click on Solve, and it says it found a solution. You want to take it, and I say OK. All right. So those lines are, again, right on top of each other, and from this we may not be able to see if the traditional lift or the new lift is any better. I mean, you can look at, even at 10 degrees, you know, we're talking about the difference between 1.46 and 1.456. You know, on a plot, that's very difficult to see the difference. But look at this error. Look at our error. It is e to the minus 23. Where this error was e to the minus 6, so this is much larger error. And then my RMS is on the order of e to the minus 12. Well, machine precision is e to the minus 15 or 16. So you can see that we are almost getting double-digit precision, that these values here are matching the original lift coefficient almost out to double precision. Okay, so anyway, what we've shown here is that yes, indeed, this data does, to double precision, match this equation perfectly. It does not actually perfectly match the traditional lift coefficient equation, and we would expect the same actually for the pitching moment. These both come from thin airfoil theory and make a lot of approximations in there, including a small angle of attack, which you can see here. See, this conformal mapping theory does not include a small angle of attack approximation, so you can see that sine alpha is still in there. And actually, there is a way you can work through thin airfoil theory to not include the small angle of attack approximation, and you actually do end up with an equation like this. So you can get there from thin airfoil theory as well. It's just not, traditionally, you apply a small angle of attack and come up with these relations here. Now you can see that they're not really that far off, and again, you know, on a plot we may not be able to see the difference between these two, but when you're trying to study theoretical aerodynamics, little differences like this can be important, and just in our understanding of what's going on. And so that's what we've demonstrated here, but most importantly, what I've tried to demonstrate is simply the process of fitting an equation to data. You know, if we have, from theory, if we know what an equation should look like, then we can get a data set here and match and come up with the coefficients for these equations that best fit this data. And we do that, in my opinion, I personally like to use the solver instead of the trend line, and of course, actually, that's the only way you can do it if one of your equations here doesn't fit one of the trend line options, which is the case a lot of times. Actually, you'll run into equations that don't fit the trendline options, and so you have to type in your own equation and use this method of minimizing the root mean square of the error in order to come up with these coefficients here.